Light always moves in a perfectly straight line. Hit a flat mirror and it bounces off with absolute predictability. The rule is simple. The angle at which the light hits the surface, the angle of incidence, is exactly equal to the angle at which it bounces off. But flat surfaces only give us exact one-to-one copies. If you bend that surface, you alter the trajectory of millions of light rays at once. The reflection scales, inverts, or flips entirely. When we curve the mirror inward, making it concave, it forces incoming parallel rays to converge toward a single point. When we curve it outward, making it convex, it forces those same rays to diverge and scatter. It looks chaotic, but the math is strictly deterministic. By applying just 4 geometric rules, we can trace exactly where these rays go and predict any complex image formation from first principles. To trace these rays, we need a coordinate system. A curved mirror is a literal slice taken from a complete 3-dimensional sphere. Because it forms part of a sphere, it has a center. We call this empty point in space the center of curvature, marked C. The exact geometric center of the physical mirror itself is the pole, marked P. Draw a straight line passing directly through both C and P, and you have the principal axis. This is our baseline. If we fire a beam of parallel rays at this mirror, they reflect and intersect at a single point on that axis. This point is the principal focus, or F. For mirrors with small apertures, this focus point sits exactly halfway between the mirror's surface and the center of curvature. The total radius is always twice the focal length. We now have our map, the pole, the focus, and the center of curvature. This framework allows us to translate a physical object into an optical image. An object emits millions of light rays, but we only need to track 2 of them. Where those 2 rays intersect after reflecting, the image is formed. Here are the 4 tracing rules. Rule 1. Any ray traveling parallel to the principal axis will reflect downward, directly through the principal focus. Rule 2 is the inverse. If a ray passes through the focus first, it reflects perfectly parallel to the principal axis. Rule 3. Any ray passing through the center of curvature hits the mirror dead on. It has an angle of incidence of 0, so it reflects straight back along its original path. And Rule 4. If a ray strikes the pole obliquely, the principal axis acts like a normal line, and the ray bounces off at a symmetric angle. Choose any 2 of these 4 rules, apply them to the top of an object, and their intersection will pinpoint the exact size and physical location of the resulting image. Let's test the algorithm. We will place an object far away from a concave mirror and move it systematically closer to see how the intersection point responds. Position 1. The object sits far beyond the center of curvature. We trace a parallel ray through the focus and a second through the center. They intersect below the axis between C and F. The image is real, inverted, and smaller than the object. Position 2. We move the object precisely to the center of curvature. The intersection point shifts to a line perfectly beneath it. The image is still inverted, but now matches the object's exact size. Position 3. As the object slides between the center and the focus, the intersection pushes further out. The image projects past C, and it is now mathematically enlarged. Position 4. We hit the phase boundary. When the object sits directly on the focus, the reflected rays emerge perfectly parallel. They never intersect, meaning the image is formed at infinity. Position 5. We cross inside the focus. Now the reflected rays physically diverge. They will never meet in real space. But if we extrapolate them backwards, they intersect behind the mirror. This creates an optical illusion. You see a virtual, erect, and highly enlarged image staring back at you. This table from the physics source material confirms our derivations. We see the clear progression of the image from diminished to same size to enlarged and finally to virtual, dictated entirely by crossing the focal point. By manipulating distance, the concave mirror yields a massive operational range, shifting from shrinking real projections to magnifying virtual ones. Now we invert the system. A convex mirror curves outward, meaning its geometric center and its focal point physically exist inside the curve, behind the surface. We apply Rule 1. An incoming parallel ray hits the curve and scatters outward. If we trace that diverging trajectory backward, it aligns perfectly with the hidden focus. We apply Rule 3. A ray fired directly toward that hidden center of curvature hits the curve head-on and bounces straight back. Where these two backward traced lines cross is where the image forms. Because of the outward curve, no matter how far away or how close you move the object, the intersection point of these diverging rays is geometrically trapped. It will always form between the pole and the focus. This chart proves the strict limitation. A convex mirror has only two operational states, an object at infinity or an object at any finite distance. In both cases, the image is virtual, erect, and diminished. The convex geometry physically prevents the formation of real images, but by compressing the visual field into a tiny, upright virtual space, it provides the consistent, wide-angle view we rely on for security mirrors and driving. Two mirrored curves, two entirely different sets of optical behavior. The concave shape bends light to project and magnify, while the convex shape scatters light to shrink and compress. The geometry reveals the exact boundary between reality and illusion. Real images are physical points in space where light actually converges. Virtual images exist only because our brains trace diverging light rays straight backward into a space they never actually entered. From the vast curved dish of an orbital telescope to the small dome mirror in a parking garage, these optical behaviors are strictly deterministic. We are just applying 4 geometric rules to a curved plane, predicting exactly where the light will land.